Now let's really get into the proofs of the consistency and liveness properties that are satisfied by longest chain consensus. So let me remind you of the story so far. We introduced this really key definition of a sequence of leaders being W balanced. So remember the way longest chain consensus works. It operates in rounds. In each round, a single leader is chosen. That leader might be an honest node or it might be a Byzantine node. And a given sequence of leaders, right? So like run the protocol for a long time, look at the leaders that get selected in each round. We call that sequence W balanced if in any window of W or more consecutive leaders, it should be the case that a strict majority of those W leaders are honest, bigger than 50%. Strictly less than 50% of the leaders in any length at least W window should be Byzantine. Very early on, we observed by the nature of longest chain consensus, if you ever have a window where you have more Byzantine nodes than honest nodes, well, then you've definitely got problems, right? It's going to be the case that because the Byzantine nodes outnumber the honest ones, they can in effect cancel out the last few blocks on the current longest chain. The number of blocks that they can sort of cancel from the end of the longest chain depends on how big the imbalance is between the number of Byzantine nodes and the number of honest nodes. So that tells us that lack of balance is an obstruction to getting what we want, to getting, for example, any kind of finality property. It also showed us, that argument showed us that, there's no hope of proving anything really about longest chain consensus unless the fraction of Byzantine nodes is strictly less than 50%. What remains to prove is that, balancedness of the leader sequence is not merely a necessary condition for having consistency and liveness guarantees. It's also a sufficient condition. That is, lack of balance in a sort of window is the only obstruction to the properties we want of longest chain consensus. So we're going to be proving that longest chain consensus satisfies all kinds of nice properties as long as the leader sequence is balanced. So in this video, let's start with the first of those properties, usually known as the common prefix property. So for this theorem, let's assume that the leader sequence, for whatever reason, maybe because it's random leaders or maybe for some other reason, but for whatever reason, the leader sequence is balanced. And let's specifically actually say it's quantity 2k plus 2 balanced. Now, in addition, we have those 5 assumptions that we laid out early in this lecture, in lecture 8, assumptions A1 through A5. Now, if you go back and look, A2 and A3, they were actually about the integrity of the process that selects leaders. And so here we're just starting from a balanced leader sequence. So we kind of don't have to worry at this point about how those leaders got chosen. So we can ignore assumptions A2 and A3 for the purposes of this result. Assumption A1 that states that the genesis block was honestly produced. That's going to be important in this proof, as we'll see. Assumption A5, which is the one that says that we're in the instant communication model. Messages between honest nodes get delivered instantaneously. So in effect, all honest nodes know the same things at all times because they can just immediately share information. That assumption, we'll use it in the proof. That is going to be for convenience. I think you'll get some intuition from this proof, actually, that it wouldn't be that hard to relax assumption A5 to the standard synchronous model as long as the parameters are chosen appropriately. But so we're going to do the proof in this video under assumption A5. And then assumption A4 is also going to be important, right? So the basic assumption A4, which is relevant for kind of all of the scenarios of longest chain consensus we're interested in, says that, it says something a little bit stronger than a Byzantine node can only add one block to a given chain. It says the slightly stronger statement that actually, while a Byzantine leader maybe could create a large number of blocks, each of those blocks has to name as a predecessor a block that was produced in some strictly earlier round. And actually, we're not going to prove in this video Theorem 1 under that assumption A4. We're going to use a stronger version, A4 prime, which does hold, as we'll see later, in the proof of work setting. So in the proof of work implementation of longest chain consensus, as made famous by Bitcoin, it's true not only can a Byzantine leader only add one block to any given chain, actually a Byzantine leader can only add one block, period. So it's going to be actually literally impossible for Byzantine nodes to produce more than one block in a given round in which it's the leader. So that's going to be the stronger property A4 prime. And under that combination of assumptions, we will, in fact, prove the common prefix property. So what does the common prefix property say? Well, it says no matter what happens, so in other words, like no matter what in-tree, call it capital G, all the honest nodes might know about, So no matter what happens, the in-tree that all of the honest nodes know about, the notation B sub k of G will be well defined. And again, remember that what that means that it doesn't, if there's multiple longest chains, it doesn't matter which one you choose. After you lop off the last k blocks, you get the same thing. Equivalently, any two longest chains agree in everything except possibly up to their last k blocks. All right, so I need to make several comments to help you parse this theorem statement. One thing I want to point out is we're actually already using assumption A5, the instant communication model, to keep the statement of this theorem pretty simple. Right, so you notice that I talk about only a single in-tree capital G, known simultaneously to all of the honest nodes. The reason I can write that, right, is because if there's no message delays between nodes, as soon as any honest node learns about something new, learns about a new block, they can instantaneously, like by telepathy in effect, communicate that to all of the other honest nodes. So there's never any sort of lack of synchronization between different honest nodes. So we can talk about the in-tree known to all honest nodes. If there were message delays, different nodes might have slightly different in-trees, and we'd have to worry about that. Under assumption A5, we don't have to worry about that. The other thing you should be wondering about is this phrase, for any possible in-tree, in Theorem 1. And so the point to realize here is that just because we fixed the leader sequence, right, which we have in this theorem, we fixed a 2k plus 2 balanced leader sequence, that doesn't actually uniquely pin down what is the in-tree capital G that the honest nodes know about. And there's sort of two things that are underspecified and that could resolve themselves in any number of ways. More obviously, perhaps, like Byzantine nodes can be doing whatever. So for different Byzantine sort of strategies of announcing or not announcing various blocks, you're going to get different in-trees, capital G, known to all the honest nodes. But also don't forget that we're also just assuming that if there's multiple longest chains, we make no assumptions about how honest nodes do that tie breaking. So honest nodes tie break arbitrarily in different ways of breaking ties, of picking which longest chain to extend. That will, of course, also result in different possible in-trees. So for any possible in-tree here means ranging over all possible things the Byzantine nodes could be doing and all possible ways that the honest nodes might break ties among competing longest chains. All right, so now that we're hopefully all clear on the precise statement of Theorem 1 of the common prefix property, let's go ahead and proceed to the proof. So the proof is going to be, you can think of it by contradiction or by contraposition, whatever you want. Basically we're going to show that the only way that B sub k could ever not be well defined, that actually you do get two longest chains disagreeing on their last k plus 1 or more blocks, the only way that could happen is if the leader sequence was not in fact 2k plus 2 balanced. So to kick things off, let's assume the conclusion of this theorem is false. Let's assume that in fact there is some outcome G such that bk of G is not well defined. What does that mean? Well, it means that the in-tree might wind up looking, it might include a structure like the orange structure I'm going to put here on the right part of the slide. Right, so just by definition of what B sub k of G means, what it means to be well-defined, if it's not well-defined, there's two different longest chains. I've drawn one ending in the block B1, a different one ending in the block B2, where they disagree on k plus 1 or more blocks at the end. So also in this structure, we've looked at the least common ancestor of B1 and B2. So if you trace back from B1 and B2 until they finally sort of resolve into the same block, right? If nothing else that happens at the genesis block, it may well happen at a more recent block than the genesis block. In any case, when you trace back and the paths finally meet, we're calling that block B star. All right, so that part I hope is straightforward. This is just what it means if the conclusion of the theorem is false. So what else is there to say? Well, you might notice I left a little white space here in the middle of the line. And so the proof's going to be, it's not going to be that hard a proof, but it's going to be maybe a little trickier than you might have expected. And the reason being is because B star, we don't know whether B star was produced by an honest node or a Byzantine node. If it was produced by an honest node, things would be a little bit simpler. But for all we know, B star was produced by a Byzantine node. Why is that a complication? Well, remember, among the shenanigans that Byzantine nodes can do, delaying block announcements is one of them. So we have to allow for the possibility that B star was created actually a long time ago by a Byzantine node, but announced to everybody else only relatively recently. And that's kind of an annoyance. As promised, the fact that blocks can delay announcements, they actually don't really have an impact. on the sort of basic consistency and liveness properties of longest chain consensus. It has implications for other properties, as we'll see later, but it does make the proofs a little bit more annoying. And so this is like one of the key points where like the fact that Byzantine nodes can delay announcements makes the proof a little bit more annoying. And so to circumvent that, what we're going to do is we're going to actually trace back even farther than B star until we get to a block where we like know what's going on, meaning a block that was produced by an honest node. So trace back from B star until you get to the most recent honestly produced block, call it B naught. All right, so how do we know that B naught exists? How do we know that tracing back from B star will eventually reach some node that was honestly produced? Well, it's kind of subtle, but this is actually where we're using assumption A1, our trusted setup assumption about the Genesis block, in effect being honestly produced, being not having a delayed announcement, being unknown to the Byzantine nodes before the protocol gets started. So if nothing else, you can trace back all the way to the Genesis block. That is an honestly produced block by assumption A1. All right, so a little more notation. So let R naught be the round in which B naught was created. Now, by virtue of being an honestly produced block, we also know that B naught was announced to everybody in that same round R naught. So not only did it exist, but all the honest nodes, other honest nodes, also knew about B naught at the conclusion of round R naught. All right, so what's the plan? Well, so remember, we're starting assuming that the conclusion is false, and now we want to go back and deduce that the hypothesis must have been false, namely that the leader sequence must not have been 2k plus 2 balanced. What does it mean to show that? It means we need to exhibit a window of 2k plus 2 or more consecutive leaders that's at least 50% Byzantine. So what is that window going to be? Well, it's going to be all of the leaders chosen subsequent to round R naught, leading up to the current moment in time, where this is the, this entry capital G is the one that's known to all of the honest nodes. That is the sequence of leaders that we will show as both of length at least 2k plus 2 and at least 50% Byzantine, which will give us the contradiction. So this is going to be a counting argument. We're just going to count up the maximum number of honest leaders that there possibly could have been after R naught, given that this is what the picture looks like. And we're also going to count up a lower bound on the minimum number of Byzantine leaders there could have possibly have been, given that the entry is what it is. It's simplest to phrase this counting in terms of heights. So let's talk about the heights of the various blocks in this orange structure. So remember what I mean by the height of a block. I mean the number of hops you need, the number of predecessor pointers you have to follow to get back to Genesis. Or equivalently, if you like, the length of the chain from the Genesis block to the block in question. That's the height of a block. So B naught has some height, call it H naught. B star has some height, call it H star. And then B1 and B2 have some height, have some common height, call it H. So let's organize the rest of the proof into a three-part claim, sort of mapping out the high-level plan that we just discussed. So as we said, the window of leaders we're interested in is the leaders that are chosen after R naught, up to and including the current moment in time, where the entry is capital G. So first we need to show that there's a sufficiently large number of leaders, at least 2k plus 2, otherwise we have no hope of contradicting the balancedness condition. And then as mentioned, we're going to want an upper bound on the number of honest leaders subsequent to round R naught and a lower bound on the number of Byzantine leaders. And so we'll show that there are at most H minus H naught honest leaders that could possibly have been chosen after round R naught. And there must have been at least H minus H naught Byzantine leaders chosen subsequent to H naught. And the thing I want you to notice is that if we can prove all three parts of the claim, we are done. We are done with the proof of the theorem. Because if all of 1, 2, and 3 hold, then there is a window of length at least 2k plus 2 that is at least 50% Byzantine nodes. And that is exactly what it means to violate the balancedness condition. So at this point, you can forget about the statement of theorem, and we can just focus on the statement of the claim and the three parts of it that we need to show. So let's start with the first part, which is not particularly hard. The first thing to observe is that if you look at all of these orange blocks, okay, after B star. So if you look at any block that points to, that has B naught as an ancestor, I claim all of those blocks must have been produced in rounds after R naught. So this is where we're using the fact that by our choice of B naught as a block that was honestly produced. Because round R naught, that was the round in which all of the honest nodes first found out about this block B naught. But because that block was honestly produced, R naught was also the round in which it was created. Okay, it was not, B naught was not somehow like a delayed announcement of some block that had been created long ago. Now, for a leader to produce any of these other orange blocks on this picture, to have B naught as an ancestor, well, they must have knew about B naught's existence for that to be true, right? You can't point to B naught if you don't even know about it. Nobody knew about, honest node or Byzantine node. Nobody knew about block B naught until round R naught. So all of these things that are after B naught had to have been created in rounds after R naught. So that's the first thing. All this orange stuff after B naught must have all been created after round R naught. The second thing is there's a bunch of stuff, right, after B naught. We have these two different longest chains, one ending in B1, one ending in B2, and they differ. They have completely disjoint sets of their last k plus 1 or more blocks. So that means there are, at the very least, 2k plus 2 distinct blocks in the orange structure, 2k plus 2 blocks that were created after round R naught. And now, to finish part one of the claim, we're going to invoke this assumption A4 prime. So the stronger assumption of assumption A4, the assumption that each leader can produce only one block. It's not the last time we're going to use that assumption. We're going to use it kind of even in a even more critical way in part three of the claim, but it's convenient to use here. Look, there are these 2k plus 2 or more blocks after B naught. A given leader can only produce one block under assumption A4 prime. I guess there must have been at least 2k plus 2 leaders chosen after round R naught, which was part one of the claim. Moving on to part two of the claim, let's first pause to state a proposition. It's quite simple. It's going to be very useful here. It'll also be useful later in our liveness analysis of longest chain consensus. The proposition states that under our standing assumptions here, the heights of honestly produced blocks are strictly increasing. Okay, so if node number 17 is honest and produces a block at height 21, and at some later point, some other honest leader, say node 23, produces some honestly produced block, that's going to have height 22 or perhaps even larger. So this proposition basically follows from assumption A5, the fact that we're in the instant communication model, and as soon as any honest node produces a block, all of the other honest nodes immediately, as if by telepathy, know about that newly created block, along with the sort of the fact that honest nodes, by definition, always extend the end of the longest chain. Right, because suppose you're an honest node, right? So your node sort of, I don't know, number 17, and there's some round, I don't know, round number 23 that you're selected as the leader. So what are you going to do? You're going to scan the blockchain. You're going to scan the entry of blocks that you know about, and you're going to extend the longest chain. Equivalently, you're going to look for the block in that entry with the highest height, and you're going to tack on a new block at the end of that. So for example, if you look at your entry and sort of the highest height you see is 12, equivalently the length of the longest chain is 12, you're going to stick on a height 13 block at the end of that. Right, so now suppose some other honest node is selected as a leader in some subsequent round, in round number 40 or whatever. Right, well, I mean, because we're in the instant communication model, right, so that later honest node knew immediately about your height 13 block that you created and tacked onto your entry. So it knows it has the option of extending a block at height 13. Now, in the meantime, okay, leading up to round 40, maybe there were sort of blocks of even higher heights created. But in any case, that later honest node is going to tack its block onto the end of the longest chain. At a minimum, it has the option of extending your height 13 block, in which case its own block will have height 14. Maybe its block will have an even higher height, but it's certainly going to be higher and in particular distinct from yours. So that's why over time, if you look at the sequence of blocks that were honestly produced, every single one will have height at least one more than the previous one. So that's sort of the brief detour into the proposition that I wanted to do. Again, we'll use this again later in this lecture in the liveness analysis. But for now, let's just show how part two of the claim follows quite quickly from the proposition. Part two of the claim, remember, says there could not have possibly been more than H minus H naught honest leaders chosen subsequent to round R naught. So why is that true? Well, suppose B naught is at height 24, and B1 and B2 are at height 40. So there's a gap of the sort of 16 kind of heights in play after B naught. Now, the node B naught, right, it was honestly produced in round R naught. It was announced to everybody, so all the honest nodes are totally aware of this height 24 block B naught by round R naught. What does that mean? So think about an honest node that's selected later, okay, in some round after R naught. It knows in particular about a height 24 block, B naught. It's going to extend the end of the longest chain. It's going to produce a block that has height 25 or higher. Okay, so every honest node selected after H naught will contribute a block somewhere between the heights 25 and 40 inclusive. The proposition tells us that there can be only one honestly produced block at each height. Okay, you can never have two honestly produced blocks at exactly the same height. So between the heights 25 and 40 inclusive, those 16 different sort of height levels, there's at most one honestly produced block in each, so at most 16 total. So that means at most 16 honest leaders could have been possibly chosen after B naught. And in general, that 16 is just H minus H naught, the gap in heights between the end of our orange structure and the beginning. So how about part 3? So now we want a matching lower bound on the number of Byzantine leaders. You want to show that there must be, for this orange structure to possibly exist, it must be the case that at least H minus H naught Byzantine leaders were constructed after round R naught. So if we have at most 16 honest leaders, we need at least 16 Byzantine leaders. That will give us the at least 50% Byzantine window that gives us the contradiction with the balancedness assumption on the leader sequence. So why is that true? Well, let's just look at this orange structure and let's just count up how many of those blocks must have been produced by Byzantine leaders. So let's do this counting in two parts. Let's look separately at the stem of the orange structure between B naught and B star, and then the sort of two branches of the fork. Well, you know, how did we define B naught? We said, well, start from B star and trace back until you find an honestly produced block, and then stop. Okay, so by virtue of stopping at B naught and not earlier, it must be that every block from B star inclusive up to the block just before B naught, they must have been produced by Byzantine nodes. Otherwise, B naught would have been chosen differently, would have been chosen closer to the end. So that gives us, okay, H star minus H naught Byzantine produced blocks. Okay, everything that's after B naught up to and including B star. So that sort of wraps up the counting up to height H star. Now let's do the counting for the heights after H star, up to and including height H. In other words, let's move on to the two branches of the fork, all of the orange blocks that have B star as an ancestor. Now notice B star, that's the first time, tracing back from B1 and B2, B star is the first time that those two paths meet, by definition. So everything after B star, those are completely disjoint paths, which means on each of those heights, height H star plus 1, H star plus 2, H star plus 3, all the way up to height H, there's sort of two orange blocks, right? One from each branch of the fork. 2 blocks per height after H star up to and including H. Now, what do we know from the proposition? We know that at any given height, at most one block was contributed by an honest leader. So, if there are 2 blocks at a given height, it must be that one of them was contributed by a Byzantine leader. So we have a range of H minus H star heights, okay, everything after H star up to including H. So H minus H star heights, each with 2 blocks. At least one of the blocks at each of those heights has to have been contributed by a Byzantine node. So that gives us an additional H minus H star orange blocks that must have been produced by Byzantine leaders. All right, so combining our 2 lower bounds, so our lower bound of H star minus H naught on the number of Byzantine produced blocks on the stem with our lower bound of H minus H star for the number of Byzantine contributed blocks on the branches, we get an overall lower bound of H minus H naught on the number of these orange blocks that must have been contributed by Byzantine nodes. And now here is the really crucial part where we're going to use assumption A4 prime, which again, remember, states that, you know, honest or Byzantine doesn't matter. When you're chosen as a leader, you can produce at most 1 block. So how do we use that? So here we say, well, by virtue of there being at least H minus H naught different blocks contributed by Byzantine leaders, if each leader could only contribute 1 of those blocks, there must have in fact been H minus H naught different Byzantine leaders responsible for contributing all of those blocks. That is a statement we could not make if we only were using the weaker assumption A4. If we were allowing Byzantine leaders to produce multiple blocks in the same round, this is the part of the counting argument that would break actually kind of badly. But under the stronger assumption A4 prime, actually we're good to go. We know there's at least H minus H naught blocks. That means there must have been at least H minus H naught Byzantine leaders. And again, as we noted earlier, all of those leaders must come from rounds after R naught because the block B naught was honestly produced. In fact, a good homework problem, if you really want to understand this stuff deeply, is to show by explicit counterexample that this theorem 1 is actually false if the only thing you do is erase the prime from A4. So if you keep the balancedness condition on the leader sequence the same and assume nothing else about the leader sequence, and you replace A4 prime with A4, in fact, the theorem is false. Again, as we discussed in that sort of short interlude video, that doesn't bother us so much because you can reprove Theorem 1 under the weaker assumption A4 if you're willing to make a stronger balancedness assumption about the leader sequence. And we're not really bothered by that stronger balancedness assumption on the leader sequence because that's also going to be true with high probability for random leaders, which is really kind of the method of leader selection that we're most interested in for longest chain consensus. So that completes the proof of Theorem 1 of the common prefix property. So again, just as a review, it was by contradiction. So we assumed that BK of G was not well defined. What does that imply? That implies you have an orange structure like the one on the slide in your entry. And then we proceeded to show that the leader sequence could not actually have been 2K plus 2 balanced. How do you show something is not W balanced? You exhibit a window of leaders of length at least W that's at least half Byzantine. What was our window? We just looked at all of the most recent set of leaders that had been chosen, basically. Everything after R naught, the round in which this honestly produced block B naught, sort of anchoring this orange structure, was chosen. So it's just the most recent leaders immediately after, starting immediately after round R naught. And we showed that the only way this orange structure could possibly exist is if, on the one hand, there's been a lot of rounds, at least 2K plus 2 rounds, so it is a long window of leaders. And moreover, because there can't be too many honest nodes and there must have been a lot of Byzantine leaders, the window must have been at least 50% Byzantine, completing the contradiction. So having conquered the common prefix property, we're going to move on in the next video to finality. Actually, we've done all of the hard work for finality already in this video. We'll see that actually there's a very quick argument that finality really just follows from the common prefix property. Once you have the latter, you have the former. And then we'll move on to liveness and the strengthening of liveness called chain quality. But I do think, of all the proofs, this one probably teaches you the most. And I think you really see how the various assumptions that we're making, kind of work together as a team to sort of force this common prefix property, which again is the key to finality, force that property to be true. Okay, so that's it for now. I'll see you in the next video for the finality argument.